Cool. We'll have more quizzes. Well, many more quizzes. I'll probably drop your lowest quiz, something like that. All the feedback in here is just to get better. That's our goal. So let's make this is. Do me one favor, when you submit corrections, please put the problem number on it. Just because I don't know if you've noticed in the grade book, I'm just using the problem number to record this stuff, and so it just helps me keep track. Because I've never done this before. It's kind of weird. So let's say homework. I'm not even gonna say number 3, because kind of each problem stands on its own, but whatever works. 7.4, 8.1, just B. 8.2, just B. 8.4 and 8.10. These guys, this is pretty chill. This is find the limit. I think I better look. Because all of a sudden we jump from 7.4 to, take a look here. Yeah, okay, this one will be fun. So this one's give some examples of sequences involving irrational and rational numbers. That'll be very cool. I think you can do that. Not too. This should not be a big write-up. This should be a couple of lines. So let's see, 8.1. 8.1 is probably some limit proofs. Yeah, so this is prove a certain limit, very much like a limit I proved last class. So I'll just say that, so if you look at the video, this one's a lot like last class, slight twist to it, but honestly it should roll the same. 8.2b, this one, we'll do an example like it today. It's kind of upping the game a little bit. And then these two questions are theoretical, where you just have to prove something about an arbitrary sequence. You don't have a formula. You're just this sequence has these properties. What can we say about its limit? And that's where things get a little. I expect these to be a little challenging, and we'll talk about them. So let's shoot for next Wednesday on that, please. So do next Wednesday. Cool. Do y'all have any questions or anything you want to ask about? Maybe did the reading, hopefully did the reading. I'm going to pretend totally did the reading.
I have a question.
Ooh, you really did do the reading. Yes, sir.
So, there's two things about the, that whole convergence equation, or like this implies kind of thing. I guess so. If it's S of with the set S of n, if within the absolute value, it's S of n minus S.
Yeah.
Is S is the point that everything's converging?
That's the limit point. Yes.
Okay.
Yeah.
And then within that is we're saying when little n is greater than big N, kind of assuming that everything beyond that point is starting to converge.
Yeah.
Does that mean that big N is could you assume or say that that's the point that everything starts to converge, or
Yeah, it can be. So that's a good question. So that big N, there's infinitely many responses for that.
Yeah.
So great question. So let's say here's my limit, and then here's my plus epsilon, here's my minus epsilon, and then so I got this epsilon strip. Maybe the sequence does, maybe it's even in there for a minute, but then it doesn't fall in. Notice how it's in here, but then it fell out. I kind of want to find that location where from that point on it's definitely in there. So let's say I called this my capital N, and I say for everything greater, for all the little n greater than this, I'm inside that strip. I could also pick this n. that could, and so anything to the right, the end isn't unique necessarily.
But it's like the higher the end, like the smaller the strip becomes, right?
I like you say that. So the smaller this, let's say it backwards, because remember the strip is the call, the end is the response.
Okay.
So the smaller the strip gets, definitely the bigger the capital N has to get.
Alright.
Yeah. Does that make sense?
Yeah.
Cool. Any other questions? Is that it? Did you have others?
For that one, I think that was it, yeah.
Oh, nice. Okay. Cool. Let's do some examples. Let's take a look. I would like to see how you feel. Well, okay, let's do one together, and then I'm going to give you kind of a more challenging one to work on here. And then maybe we'll have some time to just work on stuff in class. But prove limit as n goes to infinity of n plus 3 over n minus 7 equals what? What is the limit? What's that?
Is it 3 over 7?
It is not.
3 over negatives.
It is not that either. Think large n. When n is really large, 1,000,000, what is that ratio approximately? This is good. This is why I wanted to warm up this. What's the top going to as n goes to infinity? Infinity. What's the bottom going to? Cool. So let's talk about when I have a limit, the top's going to infinity and the bottom's going to infinity. How in calculus did you handle that situation?
You can divide out the ends and then you get.
Yeah, that's one cool way to do it. So let's actually see a couple ways to find that limit. So this problem here, let's pull it, scratch over here. So we see that this is an indeterminate form. So that's what that's called, indeterminate form, because it really depends on how fast each piece is going to infinity. And this thing might be infinite, it might be 0, it might be something in between. We don't know. I mean, we do know if we have a little experience. But so Christian's saying, divide the top and the bottom by n. I think that's what you were saying.
Yeah.
And so it's going to be 1 plus 3 over n, 1 minus 7 over n. Just like that. Yeah. So then where do you proceed after that?
Well, as for both 3 over n and 7 over n, as both of those go to infinity, they both become 0. So then you've just got 1 over 1.
Exactly. So that's a really good way to do it, especially with these polynomials. You could also remember the rule that if I have a limit at infinity, so when I say at infinity, the input is going to infinity of polynomial over polynomial. If they're the same degree, it's the ratio of the leading coefficients. So there's kind of like that quick rule. You prove it basically just like Christian's proof here. What's another way? What's a calculus way? So this is that kind of calculus, but this is more like arithmetic-y way. Yeah, Camille. L'Hopital's rule. Absolutely. So I can use L'Hopital's rule. If this was x, you'd probably feel a lot better about using calculus, but we can do it anyway. So this is the same problem. That n is discrete. It's got discrete values. This n is continuous, but we get to the same place. So what is L'Hopital's rule? Tell me, Camila. That this thing.
The derivative of x plus 3 is 1.
Beautiful.
And 1.
Beautiful. And ain't that sweet? So L'Hopital's rule says derivative of the top over the derivative of the bottom. Only in these situations, that's when you can apply L'Hopital's rule, those two indeterminate forms. But just take the derivative of the top with respect to x, derivative of the bottom with respect to x. We get 1. So we actually know the answer here. We can find the limit. Now we have to prove it. So we do magic, right? We do scratch work. And we're going to keep this space clean. do our scratch work over here. Man, they came in and made this board really nice. Really quite nice. So remember your scratch work, I just want to walk you through this again, is to look at this quantity, S sub n minus s, less than epsilon. Because this is the thing we need to accomplish, and we're going to try to find how big does n have to be for this to happen. So we put that in. Here the S sub n is n plus 3 over n minus 7, and then I put in the limit. Do me a favor, do a little algebra. Why don't you just take, what is it going to take? I'm going to let you sit with this one for a second. What is it going to take to get that to happen? So your key thing is n, you want to get a single n here, has to be greater than what on that side? Just take a minute, do your algebra. Combine these, just in case you're not doing that. Don't break it into cases. In this class, pretty much avoid cases almost all the time. they got something like we could look at. You want me to give you a sanity check? Sure, let's stay with this. Just yeah, perfect. Yeah, so you, sorry, go ahead.
Yeah, that was one.
So you divided it by epsilon, awesome, and then multiplied by n minus 7 on each side. But you didn't do anything to, oh wait, let's see. I think actually, okay, no, this is, wait,
N greater than, right?
yeah, what the heck happened here?
So can you just,
That's the better route, yeah.
that's right.
Now I'm confusing those two, wait, I gotta do it in my head, so let's see. So if we flip this, we get n minus 7 over 10 greater than 1 over epsilon.
Mm-hmm.
That's the problem there. Cool, because as epsilon gets smaller, you want this quantity to get bigger, right? So
Mhm.
as when epsilon is very tiny, this will be a giant quantity over here. Now we're headed there. Yeah, so this would just be 10 over epsilon. And otherwise, yeah, you're headed there.
Okay,
But-
N greater than 10.
Yeah, n minus 7 greater than, or plus 7, like that. Yeah, good. See if you can, yeah. See what you can do. See if you feel like you can remember how to do the proof. That might be challenging. We haven't done a whole lot. How you doing, Cease?
I think so too. Yeah, that's looking good. Now it's kind of like where to go with that, right? But yeah, well, yeah, nice. How's it going? Yeah, that's right. Absolutely, that is what you want to do. Yeah, then you got a common denominator. Perfect.
Some nice stuff will happen on top then. You'll lose that in. How you doing? Yes. Yeah, perfect. Yes, ma'am. And then the ends cancel on top. That's very nice. Yeah. How we doing,
No idea.
That's a fair answer. Can I look at it?
Sure.
Let's see. So, yeah, perfect. Excellent. And now, yeah, I think you're getting yourself into the thicket here.
So I was thinking like, when we, in this class, we were gone, move things like in this direction.
Yeah.
That's kind of what I was thinking.
Yeah, and it could help that way, but I think there's a more fundamental route first that'll make life so much easier. We'll talk about it. Let's talk about it. So everybody's doing the right thing, combining these two together. I'm getting a common denominator. Good work. And so then the top becomes, the ends cancel, and it's 3 minus negative 7, so a 10 over n minus 7 less than epsilon. So you got there. Good work. Now, one of the things that always sucks about these is that absolute value. And remember that we're gonna let n be as big as we need it to be. So we can certainly assume that n will be bigger than 7, so that this thing is positive, and that just makes life so much better. So that was why I was saying, like, yeah, that gets kind of nasty with the double inequality. So let's just maybe make a little note here that we're gonna say n has to be bigger than 7, and then that allows us to just make life about 1,000 times better. Because in the end, n is gonna be like thousands and millions and billions. And as long as we're setting conditions that force n to be larger than something, that's our goal in the end. Does that make sense to everybody? How I'm arguing that? Okay, so I'm just making a little note that we will assume this. Just to be on the safe side, we're gonna write it down. Okay, so now one of the common operations you're going to do in this process is flipping both sides. So I'm going to take the reciprocal of each side. That flips the inequality.
You're gonna get lots of 1 over epsilon kind of thingies in this whole game. Let me stop. Feel good? And this is cool because now I've got n. I've got something about n. There's multiples of it. We're gonna clean that up. And then epsilon's on this side. And the n still has to be greater than something. So now it's just some simpler algebra. I'm gonna multiply both sides by 10, and then I'm gonna add 7 to each side. Now I got some. How's that feel? So we kind of have a sense of at what point is this sequence going to fall into this range. When n satisfies this, this is true. And provided n is also bigger than 7. Why does n already have to be bigger than 7? Why is that condition enough? And I don't need to say this too.
Because the plus 7
Yeah, and what do I know about epsilon?
is bigger than 0.
It's bigger than 0. So this is a positive quantity. I'm adding it to 7. I'm already saying this n has to be bigger than 7 plus a little bit. We got this. So we don't need to add that in any expressions that we're seeing. So once I do this, I'm basically going to say, this is going to become my capital N. Whatever that turns out to be, that's going to be my N. And now I come over here and unfold this backwards with language, kind of a boilerplate language. That's what you're going to get to practice a couple of times, and many more times to go. So proof. I'm always going to start with the assumption that epsilon is a positive number. Sometimes I'll assume other things about it, but for us right now, positive is going to be the perfect thing. Sometimes we'll set like an upper bound on it, but not yet. So we got this. Then assume that capital N is equal to this right side. So 10 over epsilon plus 7. So actually, I kind of labeled this wrong. This will be my N here. This is my capital N. So I saw Cormac make a face there, but that's my capital N, that right side. Now we do something that looks like we're freaking geniuses, but we're really just writing that backwards and filling in the gaps. So now watch. Then if little n is bigger than that n, we have little n must be bigger than 10 over epsilon plus 7. I'm going to go backwards, and I'm going to undo it, and I'm going to work my way back to this original assumption. So this implies that n minus 7 is greater than 10 over epsilon. This implies that 1 over, and you can do a couple steps in one if you want. I'm just going to be very careful here. Here I just flipped both sides. My goal is to get that epsilon back by itself on the right-hand side. That's where I want to end up. So that circled blue thing right at the top of the board, that's the inequality I want to get to. So now I'm going to multiply both sides by 10. Almost there. Almost there. And here would be the step that would be like pretty much almost impossible to see had you not done this yourself. So first off, we're going to note that this is positive. Since 10 over n minus 7 is greater than 0 when little n is bigger than 7, which it is. Because I'm assuming it's bigger than this. And this is already bigger than 7. This becomes, or this can be written, absolute value of 10 over n minus 7 is less than epsilon. So this statement right here, I'm justifying why I just went and slapped absolute values on there. It's because I know that thing's positive. And then, and this would ideally be all in a nice line. Lastly, notice that, and this is the magic, the left-hand side can be written as this. And I know that the thing I've got right now is this, but here's the, like, how did they get that? And it's because I started with it and I didn't show you that. So the left-hand side is actually, and we could just actually just do this, because this is equal to this. We might as well just jump to that statement. This is equal to this because I proved, I know that for a fact. That is that, is that. So see how we're covering up our tracks, right? We're kind of like walking backwards in our tracks, cleaning the ground up, looking magic. And this is what I needed to show. Therefore, limit as n goes to infinity of n plus 3 over n minus 7 equals 1. Done. Assume epsilon is greater than 0. I create an n that accomplishes the following. So look at what we've accomplished. I just want to write it up here. If little n is bigger than big N, which is 10 over epsilon plus 7, then n plus 3 over n minus 7 minus 1 is less than epsilon. So, for any positive epsilon. This is the game of proving the limits. This is what I've shown, this implication. Let's finish that up. Now I'm going to give you one. I would like you to do one for me, please. Little bit of a twist on it, not much. Not too bad. Show limit as n goes to infinity of 1 over n squared equals what? What is the limit? 0. So try to come up with a nice proof for me, but do your scratch work. What is the inequality? You're going to set less than epsilon. What will it take to accomplish that? There'll be a little bit of a twist here, but it's the same rhythm.
So that's a good, oh, did we, I wonder what they say in the book.
I think in the book they do n greater than.
It doesn't have to be a natural number.
Oh, it doesn't.
I don't know, that's what I'm wondering, I thought that's what you were about to say, sorry. Let's take a look, yeah,
I
So
think
n can be a positive integer in the book.
positive integer.
Yeah.
So yeah, so what here's a couple symbols that'll help. Well, actually, that's totally cool, Cormac. So like if I say, n has to be greater than, you know, I could even just say this.
Yeah.
And I'll just pick the next integer
That's
by
okay.
Archimedean principle.
Yeah.
Yeah. Does that sound cool? So yeah. So we'll just assume that is a whole number bigger than whatever. How you feel, Christian?
I don't know. Yeah. I think I'm going to like.
Totally you are. Absolutely you are.
Yeah, you're doing great. Solid. You're doing good, man.
Well, the limit's now 1. That's what's causing you
Oh,
grief.
that's-
Oh, you made your life so painful. Yes, friend. Yeah, it's way better than that.
How we doing, sis?
Yeah, absolutely. Nice.
Boy, that last assignment. So good.
So, if you feel like it, go ahead, you know, while you're waiting, like Mr. Cormick, you're waiting. If you want to start, check out the homework, why not, right? Because we'll probably I think that's what's going to happen next. Wait. So maybe something I said earlier, maybe this is why you were asking, Cormac. I said we can call this n, but really n it's just the thing that sits next to n.
Mhm.
Yeah, that's a better way. That's the way I should have put it. N just has to be bigger than that big N. Short and sweet. I'm happy to talk about that as much as we want to talk about it. How you feeling about that, Christian?
The proof, geez, the proof and the scratch work makes sense. I guess I'm just kind of lost on
Yeah.
how it like actually demonstrates that the limit equals 0.
Gotcha. Because, so, in the end, like, the last thing, so remember how the flow is gonna go, and let's talk about this again. And I can see why. You're kinda like, what? Seems like an awfully big conclusion all of a sudden, out of like, just a stream of inequalities. So, I can make this claim. To say this means to
Oh, to
show.
imply that.
Yeah, exactly. So this means I can show that for all positive epsilon, I can find a cutoff big N. And so I assumed this. I produced that cutoff. So this is the given, this is the call, this is my response. I've shown that response. I've at least claimed that's the response. So I claim there exists this N, so that when little n is bigger than it, this happens. So what I do is assume epsilon is positive, produce an N, and say, use this for your N, your big N. And then I show that by using that big N, I achieve this. So here, this is the S of N, this is the S, and this last statement, will always be that guy right there. You good?
I have a question.
Yes, ma'am.
In our write-up, if we do like in other words, the inequality, like final inequality, is it okay to do that? Cause in the other proof that we just gave the example of, we wrote, like, since this, when n is greater than whatever.
What did we write? I don't remember. Can I see? Yeah, let me
So
see.
here when we jumped
Yeah.
from here to the
Mhm.
absolute one with absolute value, we wrote, it's not.
Oh,
And here, we just wrote, so can we do either or do you
yeah,
want us to
absolutely.
explain
This
everything?
first time through, I was kind of like, I mean, honestly, especially early on, the more you explain, the better it'll just be for your brain. It'll make me happy too. It's cool either way, but let's over-explain. Let's do one more real quick. Just kind of a slight twist on it. I know I said it started homework for me, but I got one more. Just one more. Were you good on, is everybody good on that? Sorry, I didn't mean, I just wanted to double check. Are we good on that other proof? Okay, cool. That's a cube root. What's the limit? Your mouth is starting to make a word.
Is it 0?
It is 0. Oh, that's not the word I thought your mouth was starting to make, but yes. Well, I thought you were gonna say 1.
No, it's not. So
Yeah, it's 0. So the limit here is 0. Let's actually talk about why. Just thinking about calc limit theorems. So this is n to the 1/3 on the bottom. That is less than or equal to this. So the most that could be
is that quantity. The least that can be is that quantity. Let me stop. Do you see how I'm getting that? Just looking at the extremes of the numerator. At most 1, at least minus 1. What happens to this as n goes to infinity?
Get closer to 0.
Goes to 0, yeah, exactly. What happens to this as n goes to infinity?
Same thing.
Same thing. So, do you remember the name of the theorem that says that if I've got something between two things and they're each going to a certain limit, then this must go to that same limit? Do you remember the name of that theorem? Squeeze theorem? Or sandwich theorem? Either way. It's a way to find limits, especially when the thing is alternating. You can do it. So we know what our result is. Let's prove it now. Oh, I see what you were saying, Camila. I kind of wrote a summary sentence at the end, didn't I, in the last one? Yeah, let's do that. Let's do that. I'll do it on this one to stay true to what I started out. Oh, again, for your response. That's the stuff.
This step, or absolute value. I didn't really know what to do.
Oh, so what is the absolute value of -1?
Yeah, that's what I was assuming.
It's always one.
Yeah.
Yeah, so yeah, this one's kind of, it's nice in that way, so you can totally just go right to that.
It was just kind of like the moving backward that like, in a proof,
Mm-hmm.
does that kind of get muddy?
We'll make it,
Less so.
we'll make it less so in our
Okay.
words. And this, I would say, assume n is greater than that, because this might not be a whole number, and the capital N is, so we're gonna assume that n is greater than 1/epsilon cubed. Yeah,
Or, because don't I want like n to be equal to this side of the equality so that like when I do n is greater than, like little n is greater than big N, I get this, right?
You do, but
So, and, so like we did here, we chose n to be any natural number
Oh.
bigger than that. And then the little n even moves further
Okay.
than that point.
Alright.
But this big N we're assuming is a natural number, so we don't wanna set it equal to something that's probably pretty weird and messy.
Okay.
So just, you can't go wrong by moving further right.
Yeah.
Always
That
makes,
makes- that makes
does that make sense?
Yeah.
Yeah.
Well, like as far as like, I guess kind of like connecting the concepts, like
Yeah.
this is kind of functions as like big N, right?
yes,
Okay.
yeah, essentially, yeah. And so we're just like, as long as our cutoff point is bigger than that,
Mhm.
we're good to go.
Yeah, like you can keep moving, yeah. that does make
100%,
sense.
100%.
I get where you're coming from. I guess it was just kind of like the connecting things that I was.
Yeah,
getting a little
that's
murky
cool, that's
on.
what we're working on.
Sweet.
Does that feel a little better?
Yeah,
Okay,
much
awesome.
better.
How you feeling, Camille? Okay, awesome. Cormac, I'm good on this?
Think so.
Yeah, that looks good. Like how that zero just kind of slipped this way. Yeah, it did. Yeah, it's good. Yeah, nice, good work.
Yeah, you are. Yeah, you're rocking it. Awesome.
Doing good, sis.
Yeah, absolutely. And then for that, like, just the next step is gonna be, put that in, you might want to, so you're, I think you're like right here. Oh, wait, you know, let's see where you were. Oh, that's just, is that your scratch work, or let's see, so what did you do, see, let n, so, also, let n be bigger than that number, because big N is a whole number, and that 1/epsilon cubed might be a really weird non-whole number. So as long as we pick something bigger than that, so kind of like we did, where I said let big N be bigger than 1/√epsilon. Does that make sense? So it's kind of like the next biggest whole number is what we're gonna pick it to be. Okay, yeah. I think this might be the step you were kind of wondering about, Christian. Like how to get back to the
Yeah.
-1. So just simply noticing that this quantity here is completely that. And the only reason I even went to do that is because I know where I have to head, right? Does that make sense?
Yeah.
Yeah? This is good. This is good for your math brain. It's like coming and going both directions. And then I still have to slip in, therefore, I have to slip in the limit, which is luckily 0. That makes life super easy. And so I'll do, like as Camila pointed out, I should do a summary sentence like I didn't do here, so I'm going to do that here. Actually, I think putting that summary sentence is good. It just kind of helps you remember what the heck we're doing here, and all this stuff. It just makes it a more complete argument. Do you ever use the word thus anywhere but your math classes? It's like, yeah.
When we're talking about limits, are our little n's always gonna be positive, or could they be?
Yes, for us, they will definitely always be positive numbers, yes. What if we called it a little early the day after this? Would that be a crime? Anybody gonna be super upset? No? Okay. Liv, we could even do the quiz if you want. I'm totally happy to do it tomorrow too. Or in office hours. Were you coming to office hours today? Just want to do that so you can review, not like just, yeah, okay, cool, awesome. Oh gosh, yeah, dudes can take care of yourself. Anything to chat about with that proof? So it'd be really cool if on Monday you've already kind of looked at the homework, especially those last two. I think the first ones are going to be nothing after this practice, but those last two are going to require some deep thought and experimentation, and probably heading in the wrong direction a little bit. So.
Revisions to next Wednesday.
Yes. Yeah. Exactly. Does that sound good?
Yeah.
Okay.
There's a question.
Yes, sir. Yeah.
For this, it says revise, is it okay? I'm assuming I'm still.
Well, wait. Let's see here. Yeah. You don't have to revise. No, I scratched out revise.
Oh yeah.
Yeah. No, I was like, okay, it's all right. It could be more direct.
I would so.
Cormac also went that contradiction route, and I gave you guys. I was like, that's cool.
Yeah.
Yeah.
I guess like how would I go about proof well is because like.
So you would kind of construct so in analysis, construction is honestly probably the most common form of things, so a direct proof, but, so let's see, so we've got this, wanna show. Wait, no, it's different, it's this. Right, yeah, and we wanna show soup of that is A.
Yep.
So, this means, so I'm just gonna say claim A equals the soup of S. So, and then I'm going to, go to the definition of soup, which says, let A prime be less than A. So let's maybe, make a picture here. Here's A, and then by, well, see you a little later. If you, hey Liv, if you wanna come in like tomorrow, if you're feeling not good, you know, take care of yourself, we can do it tomorrow or Friday.
I'll let you know.
Okay, alright. So and then we got all the rationals in there, right? And we may or may not be able to get, well, we can't get to A because it's strictly less than. So what I do is I pick an A prime less than that. And by the density, which you used,
Yeah.
by the density of Q in R, there's a Q inside here.
Yeah.
There exists Q that sits between those two.
Okay. Alright. That makes,
And I'm done. Does that make sense?
that does.
Yeah.
It feels like I used like a lot of the same logic, it's just kind of like formatting was a little bit.
It was, yeah, and it's okay, I appreciate it. You're like going the extra mile, you're like adding the words, you're writing a lot. I appreciate it, but I think like a cool thing to start working on is streamlining.
Concision, yeah.
Yeah, precision and elegant, like just type this in the argument. Yeah. It's cool.
Yeah. No
You're
worries.
thinking, like you're putting in a hell of an effort. I love it.
Working on it, yeah.
Okay, I found the definition.
Okay.
I had used its definition 4.3. Let me make it bigger because I can't see.
Oh, okay. Yeah.
So I did. I used,
okay.
I see that the one we had written in class with the quantifiers with it.
That was the one I wanted,
Mhm.
but okay, I'll give you. Yeah, all right. But in general, we're always looking for those quantifiers.
Yeah, I thought so, but I was like, let me look in the book because I was looking in the book for all of the like
Yeah.
definitions. To
Yeah,
like,
yeah.
all the
Fair
groups
enough.
of
Okay.
them.
No, all right.
And I was like, maybe, but I
Yeah.
wasn't sure.
That's cool. If you ever if you're ever unsure, shoot me an email. You know, we can
Yeah.
definitely clear stuff up. But okay.